Is everybody okay with factoring, finding the factor that we reduced out of here? Did everybody find this point of discontinuity? Yep, so that's not so bad. You can even approach it on your calculator like I showed you yesterday. If you did a calc value of 3, the y value is blank. There is none because it's a denominator restriction. If you do 3.00001, 2.99999, they will approach the same y value. That's why we call this a removable point. And at the end of the year, we'll hit these again when we hit your first lesson of calculus. But I like to remind you all year, these are what we actually go for. These are what we call them.
It doesn't have a max or min, right?
This does not have a max or min. No. No max or min on this guy. I could fit this in a little bit better.
Yeah, we did that.
Oh, okay. So where was it? Not exactly fitting. All right, we'll have to move it later, but we'll have to get to that part. Everybody good with the domain? The domain came right from your denominator. You couldn't use these values. Take them out of your domain. The range, don't do the range until the end. Your point of discontinuity has to be removed. Okay, you already removed your x value because it was in your denominator.
Yeah, I'm saying that domain.
The domain comes from your denominator. Oh my goodness.
Gross.
I'm telling you, my board is definitely haunted.
Just breaking by a new one.
Yes, please. You know how long it took to get this one hooked up?
Sorry to wait another year.
Yeah. If you ever went into Miss Fleming's old room, she had the original one that was on its own stand, and it had this big humongous stand thing, and something went wrong with it, and nobody fixed it. So she had this big monstrosity in her room, and nobody would fix it. So, John, denominator. Denominator says I have a restriction. Factor, set them equal to 0. So when you factor them, you can't use a 3, you can't use a -2. Remove them from your domain. What happens now is, if you watch this, the 3 and the -2, once we reduce this, the 3 will be removed from this right now. The -2 is what's left, and that's what comes out as a vertical asymptote. That we can't get rid of. But the point that we can reduce, a point, is called a point of discontinuity. What happened is, I would have been able to put my pen down, I would have been able to keep on going and be continuous all the way around, but I didn't. I had to come down here, stop, jump over this point, and then continue. This is where this is discontinuous. So that's called the point of discontinuity. I had to pick my pencil up and go over it. Now, we take care of it in the y, in the x's. The y's, we have to take care of it as well. So now when we do your y's, we're coming up here. We're going to get stuck right here. We can't use 1. We got to jump over 1. Because that's an asymptote here. We found that to be your horizontal asymptote. Then we come up and we say, whoops, I got to jump over this particular point. What's its y value? Its y value was 9/5. So you go from 1 to 9/5. Jump over this, and then 9/5 to infinity. This is your range. Your range, your concavities, do them at the end. Is everybody okay with your zeros of your numerator? Everything is after we reduce it. The only thing you want to hit, you want to make sure you hit your domain. Hit your domain before you reduce it. I like to say also hit your y-intercept and hit your horizontal. It kind of makes a little bit more sense. Your point of discontinuity, your y-intercept, and then we hit your concavity. Now,
how do you have a point of discontinuity up there and down there?
Well, I just say, remind yourself that this is going to be your point of discontinuity. And put it down somewhere so that you remember.
You just wrote it and then you moved it.
Yeah. Because what happens is, and it happens, I've taught this for many years, kids do this. They put a line through this, so they've crossed it out, and they never go back to it. Because it's gone. It's out of my reduced function. So, like I said, circle it, put the words point of discontinuity, so that you remember. What I myself like to do, I like to just bring it down to another place so that I remember to do it. Uh-huh, I'm gonna. So now, concavities. They're increasing, decreasing. So let's work this with, okay, good. Concaves. This is a concave down. Yeah, it kind of keeps on going, but this is what we call a concave down. No max, no min. So from negative infinity to where I hit this x value. This is my asymptote. This is where x is negative 2. So from negative infinity to negative 2, I'm concaving down. This guy is a concave up. But I got a little point that I have to jump over. So from negative 2 to that x value, which is 3. From negative 2 to 3, jump over the point. Then from 3 to infinity. You've got to jump over that point because it's not there. It's a point of discontinuity. We had no increasing sections. We had 2 decreasing. And again, it follows the same as your concavity. It makes the same cave format. You got to jump over that point. That point is not there. That doesn't exist. We call it a removable point as we approach it from both ends, but it still does not exist in your graph. Good? Nope, no max and min. Because these guys, and sometimes it's hard to see on your calculator because they sometimes just end off, but they approach this, they keep going up and up and up. This keeps going lower and lower and lower. So there's no max and mins on this. Yes?
So can you explain the concave up part of it again?
The concave up. This part here is the concave up. Where's mine? This part here is the concave up. We consider this concavity. Now, when we do concavity, we chart from left to right. We do the x intervals. So coming from here, we started at negative 2. We're moving along. We're concave. This is a concave up. We're moving along, but this point does not exist. So we have to stop, jump over 3, and then keep on going. No different than when you do a domain and you jump over the point that you can't use.
So you stop at the point with this.
Of discontinuity.
So you always hit the X part of it.
Always the x.
Oh,
Increasing, decreasing concavities always go by x.
Yeah, that was my problem. If I put 9 this instead of 3.
Yeah, do the x. Good. This was a nice little one. Didn't have any crazy things going on in there. All right. Then this was just a regular one. Everybody okay with this one? Now you appreciate these a little bit better. Hmm?
You already did it.
Oh, we already did this? Okay, I'm sorry. That was a slant. That was a slant. Here's another point of discontinuity. Okay, again, once you factor, you're going to reduce that. When you take this out of the numerator, a 1 is left. You want to keep track of this. This is your reduced format. Find your domain first before you remove your point of discontinuity. Make yourself a little note that you need to come back to your point of discontinuity. You have to use the reduced form because if you put it in the original, it's undefined. So that kind of gives you a heads up. Whoops, I got to reduce it. And then from your reduced form, find your asymptotes. Your horizontals are probably easier to find from the very beginning. For horizontal, the degree in the numerator was less than the degree in the denominator. Even when you reduce it, it comes out the same. Then your intercepts, whichever way you want to do that one, from the beginning one or the reduced one is fine. Again, concavity and increasing, decreasing have to jump over that point. These are both decreasing, except for this is wrong. These are wrong. Concave. These are wrong. Let's fix our concavities. Sometimes I take the answers out of the book, and the book usually is wrong. So why is decreasing wrong? What does decreasing do? Give me a decreasing one. What's this interval for decreasing? Negative infinity to 0. Fais-moi. 0 to 3. 3 to infinity. Again, you have to jump over that point. Okay. Do I have a range out here?
I know that the 3 is the,
You know what? I think somehow this is definitely does not belong to this. I think something happened in my thing. So let's walk through this. How do I know what?
oh, never mind.
So let's do concavity. Concave up is going to change. It's going to be the same as this one. And obviously that is still not my range. I don't know where that piece came from. So let's find the range to this guy. What's the range? Start at the bottom. Where do I get stuck? Just trace it. Trace it with your pen. Come up from the bottom. Whoops, got stuck at this point. Got to jump over the 0. I keep coming up. Whoops, there's a value I got to jump over. What's that value of that y value? 1/3. If you gave me 0.33 or you gave me 1/3, it doesn't matter. We go 0.333, go to 3 decimals, or that was a nice fraction, whichever one you prefer. And then jump over that, and 1/3 to infinity.
What's the concave of?
Concave up is the same as your decreasing this part here.
Oh, same.
Nope. It's from 0, it's just this piece right here. 0 to 3. If you're coming down, you're going to get stuck right here. And then 3 to infinity. Your domain, did I get the right domain here? Yeah. Your domain and your increasing, decreasing concavities should all tie in. They should all be complete. By the time you go through all your concavities, all your increasing, decreasing, you should have covered your whole domain. Your range, wait till the end, because we got to take out whatever points we find. Good? I don't honestly know what's underneath this. Oh, there's my range. There's my range. I don't know what happened, where that other range came from. Okay. All right, let's hit that other one. That last one is what we did in class. I wanted to do that one first. I figured if I did the hardest one with you, when you do them, they won't be so bad. This is very similar to the one we did in class. Very similar. Except it didn't have a max or a min over, or it might have over here. It had a relative min. It's got one over here. Again, the book probably doesn't have it. I like this book, but a lot of times it doesn't have the right answers in it. I should have checked it. All right, so let's hit this guy. Again, you can cross a slant, you can cross a horizontal, you can never, never, never cross a vertical. A vertical comes out of your denominator. And again, you've got a point of discontinuity on the one that you reduce. Do your domain first. Figure out all your values that you cannot use in your domain. Make sure you keep track of your point of discontinuity. Make sure you give me a reduced one. And you'll realize it when you get to here, that when you get over here and you try to plug it back into your original and it comes out undefined, you'll realize that you didn't reduce it. The range, keep till the end so that we can get all the points off of here. Was there a minimum over here? It probably is. Did anybody get a minimum for here?
Do you know that's a minimum or not?
It
The graph, like,
It stops. The graph stops unless you have John's, unless you have the color one. John's is nicer. These are the hard ones. When you have a lot of things going on, these are the hard ones. When they jump over an asymptote, just be careful because they have to go over and they have to come back up. Whether it's this way or it's this way, They're going to come back up to your asymptote. So it's going to give you a dip. Look for it in your calculator. It's got to be there. It's got to be there. All right, let's see what the rest brings us. This one was nice. Did I give you this one?
Yeah.
Okay, this one was nice. Behave again. This had a max over here. A little bit of a problem right there. There's your asymptote. Once it crosses over, it's coming back down. So find that max. This one has no max or min. Okay. Intercepts, slants. Look for your slants. If you have a horizontal, you do not have a slant. You have a vertical and a slant, but not a horizontal. And your concavities were nice too. Okay, any questions on this? A has a max. Yes, because here's your asymptote. As soon as it comes over, it would keep going like this, right? If it came over. But what happens is this. Here's your asymptote. Your asymptote says, oh, bring down your ends. You got to ride along the asymptote. So it's got to come back down again. Anytime you jump a horizontal, you're going to have a max or a min. And don't do your range till the very end.
So the cross, the cross would be horizontal lines down the back.
It's got to happen. If it crosses the other way this way, then it'll have a min. When it comes back up here, it'll have a min. If it goes this way, it'll have a max. And even though you may not see it because your calculators are not that defined in these, and they're kind of a little bit, you really won't be able to tell that you went over the asymptote. What I would do is put your horizontal asymptote in your Y2, because then you'll see it better. Because when you don't see that asymptote there, it just looks like it's kind of hanging around there. It just looks like it's graphed off to the side. Put your horizontal. You can't get your vertical, but you can get your horizontals there. And always put your slant ones there. Your slant ones definitely tell you if it's on target or not. This one had just a nice point of discontinuity. Is everybody good with this? Just a little point of discontinuity. This was a nice one. So you start with your domain. Everybody get the domain? Let's walk this one through. Get the domain from your denominator. I can't use a 5. I can't use a 4. Jump over them. Just like you jump over your little point, you can just jump over those. Now, I can reduce this. This is my reducible one. This means that this is coming out. It's like that's why you're calling this a removable point, because you're kind of removing this. Here's another little trick. If you graph this original and you graph your reduced one, they look like the same exact graph. The only difference is your point of discontinuity is no longer there if you graph the reduced one. Yes?
Does the domain restriction tell you, like, where to jump up? Or is it just the point of discontinuity?
Well, your domain restriction will tell you every x that you cannot use in this graph.
So would you, like, jump over them or no?
Well, when you do your domains, yeah, because I would say this. I would take out the 4. I would take out the 5. I can't use these. So I come across negative infinity, jump over this, include this, jump over that, include this.
What about when you do the increasing?
Well, the increasing, decreasing, this will be an asymptote. This one is unfortunately a point of discontinuity. So you have to go over that one. You have to jump over. It technically does not exist. There's a point where I had to draw my graph. I say, whoops, jump over, and continue again. That's why we call this discontinuity. It's discontinuous. So that point is not there. It's like as if you took your number line and you erased it out of there. The asymptote works far nicer because then, like, this part has no other things in it. You have a nice concave, you have a nice decreasing. The only thing you have to remember for this, and put this circle on your graph so that you remember to take it out. Maybe this is where you want to say that x is equal to 4, whatever you want to say this, if this helps you. Okay, this is where your x is equal to 4. You also have to take your y out of your range, though, too. You're decreasing and you're increasing, your concavities have to jump over this part. This is decreasing. Negative infinity to 4, jump over it, 4 to 5, and I stop. Then this part continued up here because my asymptote was here. This went 5 to infinity, decreasing. Both of those sections, and I don't know why I'm off the board over here. Oh, there it goes. Both of these sections, aren't they repeated in both of these? We accounted for both. This one's here, this one's here, this one's here. It's the same motion all the way through. And all of these have to match up to my domain. I have to have included them all in my domain. You're telling me everything that you use.
I just don't know how to apply the maximum numbers to.
There's no max and min for this
I'm
then.
not saying this one. I just don't know how to
It doesn't affect your concavity, but it affects your increasing. Because think of a regular parabola. Here's my min, here's my max. So my y is increasing up to this point. Then my y is decreasing. It works the same with these. The same with this. Let's go back to this one for a second. That's a really good question. When you realize that when you jump a horizontal and put that horizontal in your calculator, you'll see it a lot better. When you jump over this has got to come back down. That has to be a max. This works great for concavity. But increasing says, oh, well, you increased until you got to this x point. Then you decrease. Okay. So the max and the min only affect the increasing, decreasing. The concavities fall right over that. The point that you have to take out of both is your point of discontinuity. The rationals are a little bit more difficult to get through. How'd you do with these guys? I think we did this one in class, right? We did that one in class. Okay, so let's work this backwards. Vertical asymptotes, I have none. Where do I test for my vertical asymptotes? Read your chart. Read your list of things. Where do I find vertical asymptotes? Denominator. So, if I have no vertical asymptotes, that means my denominator is clean. I have no restrictions in my denominator. My denominator is going to tell me you can use all real numbers. So somewhere in my denominator, I have no restrictions. My horizontal asymptote says y equals 0. Look at that chart. When do I use a y equals 0? What condition? When the numerator is less than the denominator. So if I did this, x1 over x squared, would this give me my y equals 0? This would give you my y equals 0, but what will this give me? That will give me a restriction. I can't have a restriction. So to get around this, I need to get rid of my restriction in my denominator. I'm going to work with this in another minute. But I need to get around this. There's where your plus 1 comes in. Is there any value? Let's watch this. Do I have any real restrictions here? Do I care if I add 2, or if I add 3, or if I add 4? No. You could add whatever you like. They're not all set in stone. It's not one answer. But what I'm looking for is this. Is your numerator less than your denominator? Does your denominator have no restrictions? That's what we're looking for. You just can't add anything else that it says not to add. So if it's a vertical asymptote, I say denominator. Go like this. Denominator. This is my ratio of my x's. So I know it has to be less than. Could it be any of these? Could it be x3 over x4? Absolutely. That part is okay, but it has to exist. The hard part is the one we're going to hit today with the slant in it.
You just have to give us the equation for them.
You have to give me the equation for them. Yeah. So now,
Give me the answer.
and they're gonna vary. They're gonna vary. The ones we do today will not, but the ones these were kind of vague. Because I just wanted you to get thinking about this. Vertical asymptote. Where do I find my vertical asymptotes? Denominator. So if there are none, what's my domain? If there are no restrictions in my denominator, all real numbers. We don't do points of discontinuities in here because that would be so difficult for just for these. But we will hit those. So my denominator has to have all real numbers. No restrictions. My horizontal asymptote says y equals 2. Where did y equals 2 come from? Read your chart for horizontal. A over B. So I had to have this, 2 over 1. Didn't these have to be the same? 4 over 2, that's fine. That there's not one answer to these. But what's the problem if I do this? Wait, I'm sorry? I'm going to have a vertical asymptote, right? So what should I do? What does this guy have to be? X squared, but still x squared will give me a 0. So plus 1, plus 5, plus 10, whatever you like in your denominator. But it has to have something so that you get no restriction. But now it has to change. If I change this to an x squared, what do I have to do to my numerator? X squared. Because didn't you tell me these had to be the same, so I would get a y equals 2? Could I do it 2 over 4? Absolutely. Could I do it x cubed over x cubed? Absolutely. These were just to get you thinking, where do I find these things? There's more than one answer for these. I just went the simplest route. I don't want you to think too complicated. I just want you to get them down. Now, vertical asymptote. We have a vertical asymptote. Where am I going to find these factors? In the denominator. Good. So let's make a factor out of this. So this is an x, just a plain old x, because it would be x minus 0. This would be x minus 5 halves equals 0. So we never really see this in the denominator, right? So let's get rid of the fraction. Multiply by 2. There's my other factor. So I've got an x times 2x minus 5. I have to have that in my denominator. That has to be present. Now, I have a horizontal asymptote of y equals negative 3, which means it has to look like this. It means I have to look like this. Right? I have to have the same variable in the numerator as I do in the denominator, and it has to be a 3-to-1 ratio. What do I have down here so far? 2x squared. Okay. So I definitely have to have an x squared. I never had a minus, so I'm going to have a minus, a negative. I need 3-to-1 ratio.
Oh, so,
Yes. There you go. I need 3-to-1 ratio. Yes.
In the beginning, if you had left it as a fraction, is that okay or not?
Yeah, I probably would say that's okay, but we don't really ever see those in ours. That we see them like this because then we set them equal to 0. It's just getting used to how do I solve this.
Alright.
Yeah. You'll get used to them. You'll get used to them a little bit. I think that was the last one, right? Good. Okay. All right, let's work these one step at a time. Where do I find a vertical asymptote? In the denominator. Don't forget, also, you're giving me an equation. So it's got to start like this. So what should my denominator factor be? Agree? Agree. Let's work this one step at a time. Now, my point of discontinuity is 1/6. it's a factor, what is the point of discontinuity? How do I get to that point of
So
discontinuity?
those factors that cancel.
I factor that cancel out. So my factor that cancels out is x minus 1. So I need an x minus 1 in my numerator. I need an x minus 1 in my denominator. Of the 6, we're going to have to figure that in a second. We're going to figure that's last. But we know our point of discontinuity says, whoops, it's a factor that's going to come out of here. Now, this so far has an x squared. This has an x. I need a horizontal asymptote of 3. If I just, y equals 3. If I just did this by itself, what would it look like? Well, just give me like a 3x. I want you to just think this for a second. 3x over x, right? I need my exponents to be the same. So what am I missing on the top in terms of my exponent? An x. Right now, start like this. What number am I missing? What coefficient do I need? I need a 3. Don't I need this to say 3 over 1? Good so far? Okay, so now, somewhere, if I just close it off like this, I would meet all my requirements, except for the fact that, where did the 6 come from?
Skipping from the 1 back in.
Well, we are going to plug the 1 back in, but for now, that is very good. We're going to say plus n. The 6 is going to have an effect on this. It's not going to be a 6, but it's going to affect this. So, watch, Jordan's on the right track. If we take this out, we're left with 3x plus n over x minus 2. Okay, and this is equal to my y, my f of x. If I plug the x of 1 in here, y should equal 6. So I'm going to do 3 times 1 plus n. And I'm going to solve for n. Just cross multiply. 3 plus n over negative 1. And now all you have to do is plug it back into your very original one. So I'm just going to plug it back into this n right here. If you like, it's more helpful, write the x minus 1 over itself like this. Technically, we should probably factor out a 3 and do x minus 3, so it should probably say this. But I'm not that concerned with that factor part. If you left that factor part the way it is, I'm fine with that. Because we leave this in factored form, so technically we should go to all factors, but I'm absolutely okay if you leave this in there because that shows the work that you found. Sometimes it's easier when we go back and look at it to see where, well, how did I get this? Where did I get this x minus 3? Where it really came from here. So if you want to leave it like that, I get it.